Hi, welcome to our channel. Neuron is all you need. So in this session, we are going to look at the concept of entropy. So we'll see the definition of entropy and why it is significant in the context of machine learning. And also during the process, we will see how to derive the formula of entropy and how can we apply this in machine learning problems. So if you look at the definition of entropy, entropy refers to the measure of randomness or disorder in a data set, right? It refers to the predictability and predictability of a data set. We'll see during the presentation. And why it is significant? Because entropy is very much used in the machine learning problems like decision trees and also extensively used in deep learning. Even if you refer to the LLMs, large language models, the last function that has been used in those models is entropy. Of course, there are variations of entropy, like you have a cross entropy, you have categorical cross entropy, sparse cross entropy, and binary cross entropy. There are various variations of entropy, but underlying principle is going to be same. Okay, and we'll see how to derive this entropy also. So this entropy has been concept has been borrowed from information theory, and also it is also called surprise. So we'll explain first what is information and surprise, then followed by entropy. So this is related to the concept of probability. So you all know when you flip a coin, the probability of getting head or tail is 0.5. Similarly, when you have a die which has 6 faces, so when you roll a die, the probability of getting any face, any number on that face is 1 by 6. And let's imagine there are a box full of tickets. In the box, there are 99 blue tickets and there is one red ticket. Now somebody has draw one ticket from the box. It happens to be blue ticket, right? Again, second attempt, again it has been drawn as a blue ticket. So if you draw consistently, you will get blue ticket. And do you surprise? What is your experience when you get a blue ticket? Because since there are 99 blue tickets, you'll not be much surprised, right? But when you encounter red ticket, definitely you'll get a surprise. Because out of 100 tickets, you have drawn a red ticket. So if I put it in some way, in terms of probability, the probability of getting the blue ticket is 0.99 and the probability of getting uh, red ticket is 0.01. And when you get a blue ticket, you may not be get surprised, right? But when you get a red ticket, since the probability is very less, you definitely you will be surprised. So there's a wow factor associated with the lowest probability events, right? So in other words, the surprise is inversely proportional to the probability of that event, right? If the probability is high, the surprise is low. If the probability is low, the surprise is high. So remember this definition. So if you want to say in terms of events, when somebody says sun rises in the east, probably surprise level is low because every day you see sunrise in the east. And if it's a rain, there's a rain that may happen in monsoon. Again, it is 80% probability, so your surprise is low. In case of coin, it is 50%. When somebody says it might snow in Hyderabad, maybe during summer, the probability is less and the surprise level is going to be high if that event takes place. Okay, so we can write this in terms of inversely proportional relationship. When probability of x, the surprise is 1 by p of x, right? Because it is inversely proportionate. So usually when you have probabilities, we'll apply a logarithm scale. This logarithm will not change the information content, it just changes scale, right? For example, in terms of marks, if you get somebody has got 80 marks out of 100, somebody got 40 out of 100, I can change the scale in terms of CGPA. I can convert them into zero point 0.6 and zero point 0.4. So the information retains the same, it retains, but only the scale changes. So similarly, you apply logarithm in from probabilities, and also logarithm is a flexibility in terms of in terms of expanding the formulas, right? When you say log of a into b is log a plus log b, right? Log of a into b into c, or log of p1, p2, p3. It becomes log p1 plus log p2 plus log p3. It also assists in avoiding the numerical underflow issues. Usually probabilities are very less. So when you multiply with each other, P1 into P2 into P3, so it becomes a very low number. So numerical, it gets very underflow. It's very difficult to store uh, in terms of a computer memory. So that's why I use logarithm. So when it's a logarithm of ABC, log A plus log B plus log C, it is numerically stable. Right? And so log of 1 by px, log a by b is log a minus log b. It becomes log 1 minus log p of x. Log 1, 0. It becomes minus log of p of x. So information is minus log of p of x. So this is the information theory, right? Now we'll get into the entropy. So entropy is very simple. You just have to take a average value of surprise associated in a data set, right? It is also called expected value. So expected value will become uh, p of x into log of 1 by p of x. We just multiply, right? Since log of 1 by p of x minus log, it becomes sigma of minus log p of x into p of x. So why are you multiplying with p of x? Because I want to know the expected value, average value of the surprise associated in the data set, right? Or average value of the randomness in the data set. For example, let's take class grades. So out of 100 students, let's say 90% of the students get 80 to 90 marks and 10% of students get 40 to 50 marks. So what is the average experience in the class? So what is the average randomness in the marks in the entire class? So you'll not take average value as it is, like 85 plus 45 by 2 is 65 marks. Um, it is not exact value. It will not represent the entire class, right? Because 90% of the students get 80 to 90. So and 10% have got only 40 to 50. So it will treat both groups equally. So this is a wrong approach. So the right approach is you just take weighted average, right? So 90% of the students has got around 80 to 90. So you will multiply 0.9 into 85, and 10% of the students got 45. So 0.1 into 45. So 81 marks. So this way, if you multiply these weights, right, by how many students in each group, right, group A and group B. So that will best represent the entire class. So this is the typical student experiences around 81 marks, not 65. So here what you have done, you have taken an expected value, the average value. We can also take another example. Let's say, there are two teams. One is blue team and red team, and each player has a probability of performance in a match, right? This 0.9. When I say 0.9, let's say, out of the previous 10 matches, 90% of this time he scored well, right? And 20% of this time, this player has not scored well. And on the other hand, the right hand side, the red team, almost all players have zero point 0.5 probability associated with it. So out of the 10 matches, so 50% of the time his performance is good, and other 50% of the time his performance is bad. Now, how do you calculate entropy for these two teams? So, I mean, which team is reliable, or which team is highly predictable, right? So let's take the blue team. So you apply the probability 0.2 into log of 1 by p of x, right? 0.9 into log of 1 by p of x. So if you sum all of these probabilities, all of these entropies, you will get 3.2. So this is the average surprise of the the players in this team. So this is called entropy. So entropy associated with this blue team is 3.2. Similarly, if you calculate for the red team, zero point 0.5 into log 1.5, of course, for all the players. So it results in 5.5. So the entropy related to this red team is 5.5. So that means surprise is 5.5. So in other words, the blue team is less entropy. It has less surprise, right? Whereas high entropy, right? It is high surprise. So the most reliable team is blue. So because entropy is, refers to the degree of surprise. So if entropy is less, surprise is less, right? When surprise is less, your predictability is more. The team is entirely highly predictable. So higher the entropy, less predictable the team. Now we'll see the entropy sigma log of 1 by p of x into p of x. So we'll multiply, we already know p of x multiply with the minus log p of x. So one reason we are multiplying with p of x is to get an average value associated with the entire data set. Okay. Other reason also in terms of binary entropy, let's say binary entropy. Okay. Let's take pen. The binary entropy formula is sigma I equal to 1 to 2 minus p of I into log p of I, or pi into log pi, whatever. So it becomes minus, let's say p into log p minus. So in case of binary entropy, what happens if p is 0.2, not happening the event is 0.8. So in other words, we can say 1 minus p. We know the rule of probabilities, right? Sum of the probabilities is 1. It becomes, so bear with me, my drawing is very bad. So here minus p log p minus 1 minus p into log of 1 minus p. So this is binary entropy, right? If I put it in this way, let's check, this is probability, and let's say this is entropy, and this is 0, scale 0 0.2, 0 0.4, 0 0.6, let's say 0 0.8 and 1.0. Similarly, this scale 0 0.2, 0 0.4, 0 0.6, 0 0.8, 1.0. So if the probability of event is 1, that means it is highly predictable. So the entropy is 0, right? When the probability becomes less, the predictability becomes less. And at 0.5, it becomes almost 1. Entropy becomes 1. Because when 0.5 means the both of the events are equally possible, right? So if the head is 50%, tail is also 50%, in which case entropy is high and probability is 0.5. Now, if you don't multiply with the p, if you simply rely on log p, what happens? When generally p is reducing, right, 1, it becomes at 0.5 log p, in the sense log 1 point, log 0.5 base 2, generally we'll consider base 2. So it is going to be 1, right? It is 10 by 2, right? I mean 5 by 10 or 1 by 2. So it becomes log 1 base 2 minus log 2 base 2. So it becomes okay, 0.5. What happens when probability is reducing? When p reduces, right, log p, log 0 will actually goes to infinity, right? But we don't want to happen. So we want to make the curve into symmetric, right? When p reduces, the entropy should also reduces. So that's why you multiply with uh, p into log p. So when p becomes, try to reduce 0, this may become infinity, but since p becomes 0, you're multiplying with 0. So in that case, entropy becomes 0. And it is also valid, right? when the probability of this event, let's say this is probability of plus. Here, in this case, probability of plus is 0, which means that all other probabilities minus. So in the data set, entire data set contains minus. So even in these cases also predictability is high, which case entropy is 0. So this is one of the intuition you can say. That is why the scientists have multiplied with p into log p. So here you can clearly visualize. So this is a binary entropy, right? In this case, all events are positive events, right? In which case, the highly predictable, and you don't have a surprise. Very less surprise is very less. So, right, in this case, it becomes entropy is 0, and slowly entropy get increases, because in this case, almost positive or negatives are equally possible. In which case, the predictability is not that great. Now coming down, in this case, all it has all the negative events so in this case also the possibilities, uh, probability of getting negative is high and positive is 0, so it is also highly predictable, so entropy becomes 0. Now this entropy is also refers to purity and impurity or randomness. So here if you see the events, um, red and green, so it is highly impure, right? You get these terms, impure and purity, because in case of data set, the entropy refers to the amount of purity or impurity associated in the data set. Now this is, I would say, medium impure. This is highly impure, this is medium impure, and this is almost minimum, we can say minimum impurity. So, so this is entropy. So entropy is most likely used to, in most of the cases, in the terms of machine learning, it has been used in decision trees. So if you construct a decision tree, the formula for constructing decision tree is based on entropy. Let's say this is events of, let's say, corona. So there are 12 patients having corona. Out of 12, 8 have been detected as corona and 4 are not detected as corona. 4 are negative cases, 8 are positive cases. And if you apply some feature 1, let's say temperature, and if temperature is high, out of the 12 patients, 5 patients have temperature high and 2 patients have less temperature. So that means 5 have having corona with respect to the high temperature. And here temperature is less. 3 patients have less temperature, but still they have detected as corona, and others are not having corona. Now let's apply another feature here. Let's take maybe the body pains. If the patients have body pain, they have, out of the 7 patients, 5 have having body pain, and all the 5 has detected as corona positive. The other 2, they don't have body pain, they are detected as no corona. Similarly, another feature like cough or something else, and you divide the data set into 2 groups, and this is based on the entropy formula. And if you look at, the entropy is reduces, right? The impurity is getting reduced. The leaf node here, all are having corona, 5 positives, 5s. So if some other new patient has if a new patient has visited the hospital, you just take the parameters, and the probability of getting that corona to that patient, if he has a high temperature, running high temperature and having body pains, the probability of getting corona is high, because you are getting into this bucket, right? So, so you can check out the decision trees, and you can check the formula of entropy and also information gain in the context of decision trees. And also one more thing, one more term that associated here is that homogeneity. And here homogeneity is very less, because all are different combinations. You have heterogeneous data. And once you construct the tree, it becomes at the leaf node, all are positive, and either positive or negative. That means homogeneous data. So we're getting into homogeneous buckets. This is also another term associated with the decision trees. Now in deep learning, we use cross entropy. It is same as entropy, but only formula is difference is P of x into Q of x. This both are refers to different probability distributions. we will see what is two different probability distributions. And the formula is going to be same, minus log Q of x into P of x. Let's say, for example, you have two restaurants, which has, let's say, one food item having a rating of 0.9. The probability of that item is 0.9. And when you ordered that item and you tasted, your experiences or your rating is 0.2. So that means this probability of restaurant is different, but your experience is different. Then what is the difference? What is the loss essentially? So that is called cross entropy. So it is log 1 by 0.2 into 0.9. This is called cross entropy. Why it makes sense? Generally, in case of neural networks, artificial neural networks, when you construct a network, you get a predicted probability. Your model will give a predicted probability, but actually the true value associated with that data point is a different probability, a different label. Then you would like to uh, get the loss, cross entropy loss between these two probability distributions. So that is called cross entropy loss. So that is what all entropy about. So just go through the presentation again and read out any material of entropy and cross entropy, right? And entropy is the degree of surprise. If entropy is less, surprise is less. When surprise is less, your predictability is going to be more. When higher the entropy, higher the surprise. So the predictability of the team is going to be low. So that's all entropy for this session. Okay. Thank you for watching this video.